This video is the first video of Chapter 4, Light and Electrons. So it's mostly about electrons, but we have to start our discussion of electrons by talking about light. So again, it's all about electrons. This is a nice little animation that really covers a main point of the first part of this unit. Now you see the electron, it's running around on its particular energy ring there. And notice how it gives off light and jumps down, and when it absorbs light, it jumps up. That's a key thing to remember as we move through, and we'll talk about it more and more as we go. So light, it acts like a wave and a particle, which is kind of weird. You think, well, how's it a wave and a particle at the same time? It's one of those things you just kind of have to roll with it. There's no clear answer to how this works or why it works. Scientists have just had to accept that light behaves like a wave and a particle at the same time, because if we only use wave theory to describe light, it doesn't explain everything that we know about light to be true. Same thing if we treat it only as a particle, that doesn't explain everything either. So we say it has dual nature. The word electromagnetic radiation, I'll always abbreviate it EMR, is just a fancy word for light. So whenever you hear electromagnetic radiation, just think light. So it's energy that exhibits wave-like properties. Now you got visible light, IR, infrared, UV, which is ultraviolet, radio waves, X-rays. So all of those types of light are on what we call a spectrum. They're all electromagnetic radiation. We just divide that spectrum into different chunks. The light that we see is called visible light. And I'll talk about some of the other ones in a little bit. And they all travel at the same speed, which is the speed of light. So it goes really, really fast. 3 times 10 to the 8 meters per second, or 186,000 miles per second. So think about how fast that is for a second. Count to 1/1000, and light just traveled 186,000 miles. That's really, really far in a short amount of time. So all light, again, travels at the same speed, whether it's yellow light, blue light, green light, UV light, it all travels at the same speed. So here's the spectrum I was talking about. You should have this in your note packet, something similar to this. So what we have here, let me quick get my pen lined up. Hold on, my pad is not writing, but that's okay. I think I can go without it this video. So you got a whole spectrum here, from long wavelength to short wavelength. The long wavelengths are like your radio waves, microwaves, so you see the categories up here. And then the very short ones are gamma rays, X-rays. Now, as you move to shorter wavelengths, so lower wavelengths, we say they have higher frequency and higher energy. So know these things, write these down in your notes. Longer wavelengths, higher wavelengths have lower frequency, lower energy. So the small bit in the middle here is what we call visible light. That's what our eyes can detect. They can detect those wavelengths. Now that doesn't mean there isn't light happening outside of this range. It's just that we can't see it. So we know that UV light exists because it gives us a sunburn. We can use X-rays, they go right through our bodies to take pictures of our bones. But we just can't see them with our eyes. Our eyes do not detect those wavelengths. So we have instruments that can do it for us. Okay, so wavelength. The wavelength is the distance between identical points on a wave. It's measured in centimeters, meters, or nanometers. The symbol for wavelength is this upside down Y looking thing. It's called lambda. It's the Greek letter. It's a Greek letter called lambda. And then, as I said here, centimeters, meters, or nanometers. Now a nanometer is 1/1000th of a meter. So a nanometer is really small, and we tend to measure a lot of the wavelengths in nanometers. So here's a picture of what a wavelength is. So you can measure it from crest to crest, or you could even measure it if you wanted to from trough to trough. It just has to be 2 identical points on adjacent waves. Now frequency. Frequency is a little trickier to understand sometimes, but it's how many waves pass a given point every second. So the The units are number of waves per second, which we call hertz. So the units are per second, 1 over seconds, or hertz. Sometimes you'll see seconds minus 1 used as the units. That's another option as well. So what I have here is a picture of two waves. The top wave has a shorter wavelength. Both of them are traveling at the same speed. So if we pick a point right here, imagine a wall, how many waves are passing it every second? We can see that the shorter wavelength has a higher frequency. More waves are passing every second. The longer wavelength has a lower frequency. So you can see the little red star here going up, down, up, much slower than the one is on top. So remember, high wavelength or short wavelength, high frequency. Long wavelength, low frequency. And that relates to this equation. The speed of light is equal to wavelength times frequency. So there's an inverse relationship. So if you remember chapter 2, if you multiply two variables and it gives you a constant, you know it's inverse. So that means is that if wavelength goes up, frequency goes down, or vice versa, because the speed of light never changes. It's always 3 times 10 to the 8th meters per second. That's in a vacuum, though. So there is a little disclaimer there. Amplitude, so that's the distance from the origin to the crest. That's how tall the wave is. So you take the origin, this is called the origin, the zero energy point, and then the distance to the highest energy point of the wave. You can also measure from the origin to the trough, same distance. So amplitude is how tall it is, and it has to do with how much energy the light has. So if you think about sound, low amplitude sound would sound quiet. High amplitude sound would sound loud. Louder sounds have more energy. Same thing with light. Low amplitude light would be like a dim light. High amplitude light would be a very bright light. So it indicates how much energy is being transferred by the waves. Higher amplitude waves have more energy. And think of it like this. If you're on a boat, you're in the middle of a lake, a little ripple, low amplitude waves aren't going to tip your boat over. But if you got a big storm and all of a sudden you got high amplitude waves, very tall waves out on the lake, they have lots of energy and they can lift your boat up and flip it over. So that would be another example of amplitude in terms of waves. Now there's two types of spectrums. I'm going to end the video talking about the two types of spectrums. There's a continuous spectrum and then there's a line spectrum. So the first one is a continuous spectrum. It's a spectrum where all the wavelengths in a range are included. So example is white light. Sun has all colors. So if you look at a rainbow over here, this would be a continuous spectrum. You see all the colors from purple and they blend through all the way over to red. That's the whole visible spectrum that you see. Or if you look through a spectroscope, this is what a continuous spectrum would look like. All of the colors are there. There's no gaps in the light that I see. All wavelengths are present. Now the other one is a line spectrum, or also called an atomic emission spectrum. So this occurs when electrons are promoted to the excited state. Energy is absorbed as they fall back down. They release light. This actually goes back to the beginning of the video. You saw that electron jumping up, falling back down. When it falls back down, it gives off light, and it gives off light of a very specific energy. That energy comes through on a line spectrum. So actually here is forgot I put it in the slide. So you can see as it drops down, it gives off light. Now the light that it's giving off here, so watch when it drops back down, it gives off light. That light might be this particular line. It would show up like this in a line spectrum. And now because atoms have multiple energy levels that they can drop to and from, this particular drop might correspond to this particular energy of light. A bigger drop might correspond to a different one. And I actually said that backwards, so you can call me out on that if you watch this later and you understand that. This would actually be the lowest energy transition. This would be a bigger fall because purple is higher energy than red. We'll get to that later. But the important thing I want you to know this for the test. Each line on a spectrum represents an electron falling down. So in order to see this light, an electron had to fall down, lose energy to give off this light. That's the important thing I want you to know about atomic emission spectrums. And the last thing is compare and contrast this spectrum to the continuous one from the last slide. Notice that you definitely don't see all of the colors represented here. You see 4 very distinct colors represented with gaps in between. So there's no light in between here. And we'll do a lab. Every element gives off its own unique emission spectrum. This particular one is for hydrogen. So if you get hydrogen excited, it'll give off this light, this pattern of light, and you can identify hydrogen based off of this pattern. So this is like the fingerprint of an atom. Every element has a unique pattern, and we'll do a lab where we excite some metals and some gases, and we will compare their line spectrums.